So our next conversation is about Maxwell's equations, and they're really just a collection of other people's equations for the most part. So we look at Gauss' law for electric fields, and we remember that that's the total flux of E dot dA through a closed surface is equal to Q enclosed over epsilon naught. We got another version for magnetic fields, which is as simple as saying that the magnetic flux, B dot dA through a closed surface, so a fully encapsulated sphere, cube, or something, would be mu naught times the magnetic charge enclosed. So these are electric particles, these are magnetic particles. We've got Faraday's law, which we would say is the circulation of the electric field around a closed loop, so not a closed surface, but a loop. We might call that the EMF or the voltage, and that's related to the negative magnetic current minus the rate of change of the electric flux through the area of that loop. And then the last one is Ampere's law, which is another one of these, right? The magnetic field B dot dL is related to mu naught times the electric current plus mu naught epsilon naught times the positive rate of change of the electric flux. And I'm sorry, this is a mistake. This is magnetic flux, right? So these are very beautiful, very symmetric equations, right? And this is a very nice, like I said, aesthetically pleasing universe. E and mu are on the numerator and denominator. The particles are there. Here we've got some relationship of the changing fluxes. One's magnetic, one's electric, and they produce magnetic and electric respectively. And then there's, of course, their currents and a couple of constants outside to make the units and everything work out. If you're paying attention, I certainly hope you're not taking notes, because we know that the true magnetic field Gauss law is 0. And this one, for Faraday's law, doesn't have another term in it, right? And that's because there are no magnetic charges in this universe. And that's something that keeps physicists up awake at night. I mean, it's a real problem because we see so many symmetries of things that are equal and you know, converse, or maybe they're anti-symmetric, right? Where one does something, but the other does exactly the opposite. So this is really bothersome to us, that there is no magnetic charge. You may have heard this called like a magnetic monopole, and probably in a survey of 100 physicists, you probably would get 90 or 95 that says the holy grail of our science right now would be to find magnetic monopoles, something to bring the symmetry here together. Now, you might have a few cosmologists or particle physicists that talk about grand unifying theories or the meaning of life or something like that, but no, most of us would be very interested in finding this, some kind of magnetic monopole or magnetic charge that's only north or only south and that doesn't appear in pairs. But we don't have that. We only see dipole-like fields that come from moving charges, moving electric charges here. We've never really seen one that came from just a particle this north. So let's go back through and make sure that we have this correct. Something I find irritating about Maxwell's laws is that it's just a talentless compilation of other people's equations. We have Gauss' law, and the true one, E dot dA is Q enclosed over epsilon naught. We've got the true magnetic one, where we just say that B dot dA is 0. We've got the true Faraday's law that, you know, the EMF, or in the formal sense, E dot dL, is negative d phi dt, where that's magnetic. And then we've got Ampere's law, which says that B dot dA is pretty much mu naught I enclosed. Now, I would say that Maxwell was talentless in this sense, but it turns out Maxwell kind of invented some of these other laws and just named them after other people. I'm not sure which, but I think Gauss' law actually wasn't invented by Gauss. I think it might have been invented by Maxwell. Or Ampere. I don't look it up. One of these laws, either Gauss or Ampere's law, was actually invented by Maxwell. And the important part for Maxwell's equations, his big contribution was solving the capacitor problem and adding this term, epsilon naught mu naught times the electric flux derivative over time. And this makes a correction to Ampere's law, and an important correction that baffled physicists for some time. So let's go about solving the capacitor problem on our own. And we can do this kind of from scratch. When we see current delivering charge to a capacitor, right? So let's call this the current, I use lowercase I. It delivers to the capacitor and it bleeds the energy or the current out on the other side, right? So we're building a positive charge on this side and building a negative on that side. If we were to do an Amperian loop over here, we know that B dot dA is mu naught times the current enclosed. And we can do this, and we measure true fields around that. Make sure I get this right. They look like this. And the same is true over here. We've got magnetic fields that are measurable. They do turn up over here according to Ampere's law, right? So we get B dot dA, B dot dL is mu naught I enclosed. But what's really interesting is in this region in between the plates, where there is no current enclosed, there is still a detectable magnetic field. And that's a problem. It's kind of a, what? So Maxwell solved that problem by using some convoluted math techniques, but we'll just kind of play around with it and say, what is going on in the situation? Let's just focus on the capacitor by itself. So in between the two plates, let's say there is a charge on the capacitor. And that means there's also some kind of an electric field in between the two plates of the capacitor at a particular time. And we'll freeze the time right now and just kind of do a quick and dirty analysis. What can we say about maybe the charge on the capacitor? We know that Q is equal to CV. I guess is one way we can do it, right? And C for the parallel plate capacitor is epsilon naught A over D. Okay, and we know that the field on the inside is uniform, right? According to Gauss' law for an infinite sheet, this is, sigma over epsilon naught or I guess Q over A epsilon naught, right? So these are options. But another thing we can say is that, hey, V over D for a uniform field is also an E. It's also V over D, volts per meter. So we could rewrite this and say this is epsilon naught A times the electric field. And let's think about that. If we're talking about the entire area of this plate times the electric field that's going through it, that to me looks an awful lot like an electric flux, right? All the field integrated over the area of the plate. So we could say that Q is related to epsilon naught also times the rate of change, or not the rate of change, just the electric flux. So our next question, where did this Q come from? It's being delivered by some current. And it would be really nice for us to be able to equate in some way the current delivering the charge to what's going on in the capacitor. So in that case, if we took the derivative of both sides, and we say, wait a minute, ddt of Q is I, the rate of change that charge is being delivered, then we have some kind of a current that's related to epsilon naught times the change in the electric flux, not magnetic, but electric. So the total flux of everything going on inside, its derivative times epsilon naught, is also equal to all of the feeding current that's delivering the charge into the capacitor. And it would seem that we could substitute whatever this is in place of the current, and then we can say, hey, this is related to the magnetic field. And we do that. So this is called the displacement current. It might be labeled as I displaced, and it is really related to epsilon naught times the rate of change of the flux dt. If we wanted it for the entire capacitor, so we're at some location outside of the two plates and you've got all of the flux that's changing inside, then you've got 100% of it. If you're somewhere lower than that, you would have to explicitly calculate for this area fraction to figure out how much displacement current you have at a spot. So it might give us kind of a different behavior. It might give us some R dependence in the magnetic field inside the two capacitor plates. Okay, so in Ampere's law, in the region in between, I guess let's come back here, the region in between these two plates, B dot dl is still a mu naught times I enclosed, but in this case, that's I displaced at any particular point, right? So let's just call that equals mu naught times this, epsilon naught times that. So why don't we bring it all together and just fix Ampere's law in the first place? B dot dl, and this is now called Ampere-Maxwell's law because it includes Maxwell's important contribution about the capacitor. Let's say this is mu naught times the total current enclosed. That'll be I real, or the actual current from the charges, plus I displaced. So that relates to mu naught I enclosed plus mu naught epsilon naught d flux dt. If you're in a region like with a regular wire that doesn't have this, then it's just gone. This is the the Ampere's law you're familiar with. If you're in between the two plates, you just have that. And I'd have to think of some really exotic cases that would use both. That might be something like a leaky capacitor, right? It's a really old capacitor, something that doesn't hold a charge well. So while it's got charge being delivered to it, that would look like this part. But there also could be a real current from charges bleeding off on the inside. And these two effects together would combine to give us some net magnetic field on the inside. So that might be a case. Okay, another case might be something like dealing with a solar wind or some other nonsense out in space, right? Where you have variable fields and you have a real current in charged particles moving. So that's Maxwell Ampere's law and how to deal with that. Let's say we wanted to find this situation in between the plates at some variable r. We have a known current that's coming in, that's delivering charge to the plates according to rules. And I want to know at this radius, going all the way out to, let's call this radius A, how does the magnetic field vary all along on the inside? So let's do two regions. Region 1 would be in between the plates, and region 2 would be out here. To do that, we'd have to do B dot dl equals mu naught epsilon naught d flux dt, right? And then ask ourselves, well, what is the electric field and the flux in this particular region? So let's assume that they're circular plates, and to explicitly calculate that, looks like we have B times the total area of that, enclosed region. So maybe pi r squared. Nope, because this is a circulation. B times 2 pi r equals mu naught epsilon naught times the rate of change, I guess, of this. We have the electric field times the area, pi r squared. And the electric field is uniform, all in between the plates, right? Regardless of whether we're inside or outside. Everywhere inside these plates, between the plates, has the same electric field. So that would be mu naught epsilon naught ddt of, I guess, sigma over epsilon naught. should give us some cancellation, and then times pi r squared. What is sigma? That's Q over the total area of the plates. That'd be pi a squared times pi r squared. And I still have that d dt hanging around out front. I lose some pi's. It looks like I get mu naught dq dt, and then looks like r squared over a squared. And this is what's going on somewhere, whoops. This is what's going on somewhere in between the two plates. Okay, we should simplify that. So I got b with the 2 pi r. So let's go mu naught dq dt. That's delivering the charge to the plate, so that's the real current. We get r squared over a squared, and then my 2 pi r over here, 2 pi r. A little cancellation, and finally, mu naught I r over 2 pi a squared, I guess, is a magnetic field in between the two plates in region 1. If we want to do it in region 2, that's okay. In fact, all of this stuff is pretty much the same, right? We got b times 2 pi r equals mu naught times, I guess, dq dt times the area, but what is the maximum area that has flux? There is no flux outside of these two plates, right? So our maximum amount of flux would be the electric field, sigma over epsilon naught, I guess, times pi a squared, which is, of course, mu naught epsilon naught q over epsilon naught total a, pi a squared times pi a squared. Well, this is uninteresting, right? And when we take the ddt of that, we get mu naught times the total current that's delivered to the circuit. This looks an awful lot in region 2 like just an infinite wire when you're outside of the two capacitor plates. So that's how we would go about doing it. Calculate the flux in your little region. Make a displacement current out of it according to, well, the displacement current's epsilon naught d phi dt. And we're pretty much set. Interestingly, how would we do this problem if instead we just had a big thick portion of the wire? Right, so the current's coming in, and then it kind of spreads out through the wire. And now it becomes thick, not thin. And we've done this before, right? We would find some amount of current J. So let's make this our Amperian loop. J is the total current divided by the total area, in this case pi a squared, if we keep the same values we had before. Okay, and then you want to find I enclosed according to regular Ampere's law. Well, that's okay. That's J times area enclosed, which is I over pi a squared times pi r squared, right, for this loop. Get a little cancellation. We get I r squared over a squared. So in Ampere's law, B times 2 pi r equals I enclosed times mu naught. That looks like mu naught I r squared over a squared. And then we'll divide this over and say B is mu naught I r squared over a squared over 2 pi r. And there we go. That's our magnetic field at any point inside the thick wire. We'll look at that result and compare it to what we did with the displacement current form. It's the same formula. So if you want to reimagine it this way, think, here's a real current that comes in, and as soon as it hits this capacitor and turns into electric flux, in a sense, it spreads out throughout that entire cross-sectional area. So it's kind of like a real current, or at least it's analogous to a real current. And, you know, it just spreads out, and you would treat it like you would normally if it was a true wire. But it's not. It's this new displacement current that we've invented to help us understand what's going on here. So I hope that's a little bit better, and I hope that's easier, and I hope that explains also why I was saying a change in the electric field kind of relates to a current when we talked about that comic book strip of propagating EM waves. It all comes down to this capacitor equation or capacitor problem solution. Okay. And I guess a final note that we need to remember with Faraday's law, we do E dot dl and we get negative magnetic changes. So Lenz's law opposes the change in B to generate a field E. Maxwell's isn't negative. B dot dl is positive. Epsilon naught mu naught times the electric flux ddt. So this is an important thing to remember also. Faraday's law opposes this change. Maxwell's law follows this change. And what's super interesting, changes in magnetic fields create electric fields, and changes in electric fields can create magnetic fields. And it turns out these two phenomena, electric and magnetic, are the same thing in a way. They're easily converted into each other. And you even saw that when you did the relativity problem, where we had the moving charge versus the non-moving observer. So E and B are the same thing. They just kind of depend on perspective, and they're two expressions of a very similar phenomenon. So we call these electromagnetic fields, and we call them electromagnetic radiation, and it's just a field of electromagnetism.